Yeah. So good afternoon to all. Very good evening, in fact. So welcome to the one of the live section of the NPTEL course Heat Transfer. So this is our first session. We will be starting with the week one, and the session will be. I mean, this session actually for this course there are two sessions. One in the Saturday, and also one in the after one in every Monday for 12 weeks during the duration of this course. So the basic objective of these sessions is to discuss some of the practice questions related to the contents that are taken in this course, so that this will help you in solving the practice sorry assignment questions of this course, and also the final exams and final examination of this course. So today I am so first I will introduce myself. I am Hemant D. I am a research scholar at the Department of Mechanical Engineering, IIT Madras. So I will be handling this Monday 6 to 8 p.m. session. So let's start the session. So I think we have around six people who are already joined. So okay. Anyway, I think others will join in due course. So just we will start with our session. So first we will have a overcap of what we need to just yeah, sorry for the disturbance. So first we will have a recap of what are the contents that are taken in the week one. So in the week one we had a brief introduction about the introduction to heat transfer, where the different modes of heat transfer were discussed, like conduction, convection, and radiation, and also uh, the conduction mode of heat transfer. We started with conduction mode of heat transfer, and some basic concepts were started. And 1D heat conduction equation, sorry, the general heat conduction equation was derived, and also from the general heat conduction equation, 1D steady state heat conduction equation that derived. Then the resistance concept of the heat transfer, electrical analogy uh, of heat transfer was also discussed in the week one lectures. So in this session, we will discuss some of the questions related to the these topics. So what I will do is, I hope everybody has are ready to solve some problems. Like you should have some pen and paper, and it's advisable to have pen and paper and a calculator so that you can also solve along with me. So first, I will give some time for you to solve or attempt the question. So those who are getting the answer can give in the chat box. I will give some time for solving each questions, and after that, I will solve. Okay. So let's get started with the first question. So in this question, the walls of a uh, large furnace are made of two materials. Okay. So it's a conduction problem. So a conduction in a composite wall. So this topic was already discussed in the week one. So the surface facing the high temperature environment receives heat from a high temperature source, which is at 200 to 50 degrees Celsius, subjected to a heat transfer of 45 watts per meter square degrees Celsius. And the ambient, the other side of this wall is at ambient temperature at 25 degrees Celsius and has a heat transfer coefficient of 9 watts per meter square degrees Celsius. So we have to determine what is the heat transfer per unit area. So I think I will draw the schematic, or first I that will help you to solve this. So those who you can also start solving this question. So we have a composite wall. Okay. So I will give the figure. I think some values are missing in the question. So one is the steel and other is a brick. Okay. So this is the thickness of the steel. Steel is 3 mm, and the thickness of the layer of big brick layer is 100 mm, and this is at 250 degrees Celsius, and the heat transfer coefficient is around 45 watts per meter square degrees Celsius, and this side it is 25 ambient, and the heat transfer coefficient at this side is around 9 watts per meter square degrees Celsius. Okay, so these are the given things in the question. So what we have to find out is, so there will be a heat transfer from inside interior to the ambient. So we have to determine what is this heat rate of heat transfer. That is heat flux. It's basically the heat transfer per unit area. So what is that refers to? That is the basically the heat flux. Okay, so basically we have to find out what is the heat flux in this question. So I will give some 2 3 minutes for you to attempt. After that, I will start. So uh, those who got the answer can write into the chat box. And also the thermal conductivities are missing. Right? So you can write the this I'm writing it as Ks, that is K of steel, that and also K of brick. So K of steel you can take as 220 watts per meter degree Celsius or meter Kelvin, and thermal conductivity of brick is zero point 0.2 watts per. So I think all the data is necessary to find out the heat flux is given. So now you can start solving. Yeah, I got one answer. So what about others? Yeah, I got one more answer. Anyway, okay, I think you are able to solve it. So I will start solving this out. So first we will define some temperatures here. Like uh, this is I am writing as T0. This is TC and TI, and this I am writing it as T2. That is 250. That is the interior temperature, and the ambient temperature I am writing it as T1. That is 25 degrees Celsius. So now let's draw the resistance network of this. So first we have the T2. Sorry, we have T1 this side, and we have a convection resistance that is happening, that is 1 pi H1, then T0. Then there is a conduction resistance for the steel, that is LS by KS. This is LS and LB. And there is a conduction resistance for the brick, that is LP divided by KB. And there is a convection resistance. Okay, 1 pi H2. So this is a resistance network. So what is the total resistance? R equivalent resistance is how much? 1 by H1 plus LS by KS plus LP by KB plus 1 by H2. So this is 1 by 9 plus LS is 3 mm. So writing it in uh, meters. So that's by 20 plus LP is 0.1 divided by 0.2 plus 1 by 45. So what is this answer? This is around 0.63372 is the resistance. Okay, is degrees Celsius per watt. Can write either Kelvin per watt or degrees Celsius per watt. So what is Q? Heat flux. Heat flux is equal to delta T divided by R equivalent. Okay. So what is delta T? T2 minus T1 divided by R equivalent. That is 250 minus 25 divided by 0.63372. So this will get us 355.18 watt per meter square. So this is the almost. This is the heat transfer per unit area across the wall. Now I'm giving. I want this intermediate these temperatures, that is T0, TC, and TI. So please calculate this T0, TC, and TI.
Sir, I think you should show the statement, because statement is not visible.
Is that fine?
Thank you.
Okay, anybody got this T0? At least one temperature. Anyone? T0, TC, or TI?
So T0 is coming out to be 25.
It won't be exactly 25.
If 5.1.
How we calculated that? Okay, I will do. If I am doing any, if I'm doing wrong, please let me know. So we know the heat flux already, which is 355.18 watts per meter square. So at steady state, so they means what is the convection heat transfer from this side? Means I'm first considering this side. Okay, H1 into T0 minus T1. I hope this is clear. So from this surface, we have a convection heat transfer. So H1 is already known. So first one is first we have to find out what is. So the heat flux is already known, that is 355.18, which is equal to H1 T0 minus T1. Okay. So what is T1 or T0? T1 we already know, which is equal to 355.18 divided by H1 plus T1, right? What is 355.18 divided by H1? 9 plus T1 is 25. How much it will be? Let's calculate and tell. Yeah, it's 64.45 degrees Celsius is the T0. Okay, so now we have a conduction. So T0 is already known. Okay, now there is a conduction heat transfer across this stainless steel layer. So what is, we already know Q heat flux is already known. Ks, what is the temperature gradient, that is Tc minus T0 divided by the length. This is the conduction that is happening across the stainless steel, okay, or steel. This is already known. Ks is, we know that is Ks is 20. Tc we need to find out. T0 we got 64.45. L is already given 3 mm. So if you convert to meters, this will be the expression. So what is Tc? Can you please calculate and tell? I am not getting 150. I am getting around 64.51. So please check. Anybody others? Please confirm the answer.
So 64.51.
Yeah, it should be 64.51. 64.51 degrees Celsius. Okay, now the same, right, you can apply. Either you can equate the conduction across this brick, or you can equate the, it's like the convection at the inner side. So we know 250, sorry, the heat flux that is 355.18 will be equal to H2 times T2 minus Ti. So we know H2, it's already given 45. T2 is already given, which is 250. Ti, we need to find out. Can you please calculate and say what is Ti?
So 242.11.
Yeah, 242.1 degrees Celsius. So, okay, so this is a question for this two layer, for a composite wall containing two layers. So it can be 3 layers or 4 layers. So the method is almost same. Okay, even if it is 3 layer or 4 layer, if it is a parallel wall, means if it is in series, like. So I hope you were able to understand this question. So this was a single question. So to get started with. So then we will move on to the next question. This is also a composite part. So we have to find out the overall thermal resistance. So the the schematic of the composite wall is given. Like we have a layer of material having thermal conductivity 0.02 initially. Then it is like a then the next layer is composed of two materials having different thermal conductivities, that is zero point 0.1 and 0.05, and its dimensions are also given. So you can calculate the overall thermal resistance, just the overall thermal resistance, that's all. You can try this question and let me know the answer. Okay, you can try solving this out. By the time I will also start, because we have to solve a couple of questions more. So I will draw the resistance network. So this is a resistance network. So uh, this I am taking it as L1 and K1. This is as K2. This is L2, K3. Okay. So it will be easy to uh, do the problem. So this one, the resistance is L1 by K1, and this, which is equal to R1, I'm writing. So R2 is equal to L2 by K2, and R3 is equal to L3 by K3. So we can simplify this network. This is a combination of a series and a parallel network. Okay, this is almost exactly like electrical network. So we are converting these two parallel circuits into a single circuit. Okay, I'm writing it as R equivalent. So how we write the parallel equation, that is 1 by R equivalent is equal to 1 by R2 plus 1 by R3. Okay, so what is R2? R2 is L2 divided by this can be written as A1, A2, and
Yes, the
A3.
answer is 64.28.
64.28. No,
Sorry.
please check the answer. It should be one within A, B, C, D. So L2 divided by, so I'm writing, this is not the flux, this is the actual heat transfer, because the depth and also the uh, depth of the block is given. So we can easily find out the area of the blocks. So this is A2, this is A3. So L2 divided by K2, A2. So L2 is how much? 0.25 divided by K2 is 0.1 into 1 into 1. sorry, 0.5. Okay, 0.25 divided by K2 0.1 into 1 into 1. Yeah, right. This it should be around 5 Kelvin per watt. What you can write. So R3 is equal to L3 divided by K3 A3, which is equal to, okay, similar L3 and L2 are same. K3 is 0.04, 1 into 0.5 is it comes out to be 12 Kelvin per watt. So what is R equivalent? 1 by R equivalent is equal to 1 by R2 plus 1 by R3, which is equal to 1 by 5 plus 1 by 12.5. So if you do the math, you will get R equivalent as around 3.6 Kelvin per watt. Okay. So now we have reduced the network as two series networks. This is Q, R1, R equivalent. So R equivalent we already know 3.6 Kelvin per watt. R1, what is R1? It is L1 divided by K1 A1, which is equal to what is L1 is 0.5, K1 is 0.02 into A1 is 1 into 1. Okay. This will come out to be around 25 Kelvin per watt. So the total resistance R total is equal to R1 plus R2, because this is in series. So 25 plus 3.6, that is 28.6 Kelvin per watt. Or you can write degree Celsius per Kelvin. So I hope this was clear, because first one is like series, then it's a parallel network. It's a series combination of series and parallel. So first, if there is a combination of series and parallel network, first we have to reduce the parallel network into a single network. Okay, so that I did. That R2 and R3 was in parallel, so I reduced it into a single network, right? R equivalent. So then the all the networks become series, that is R1, and R equivalent becomes in series. So just in series the resistance are added up. So I just added R1 and R equivalent. So the only task here was just to solve down this parallel networks, a combination of parallel and a series network into completely series network. So I hope you got this answer. Anybody got this answer? Is 28.6.
Sir, I was not able to understand the value of R1. How did you calculate it?
R1.
Yes, sir.
R1 is just L1 by K1 A1. It's like the normal formula.
Sir, why didn't we have taken the 0.5 meter length, like instead of we have taken one into one?
That is area. Like the area across the heat transfer. What is the area across this heat transfer? Like it is into the plane. Like we cannot visualize the area. The area is into the plane of the paper. So the width is given, the height, that is 1 meter is given, and the depth of the slab in the question is already given 1 meter. So the area is 1 into 1.
Okay, okay.
I hope you got that. Tushar.
Yes, sir, I got it. I got it.
Yeah, okay. So let's move on to the next question. So this is also a composite slab question. So actually, I think this is a gate question. So you can try this out. So in the composite slab, the temperature of the interface, that is, it's already given. The interface between two material is equal to the average of the temperature at the two sides. That is, T inter is equal to T1 plus T2. Assuming one-dimensional heat conduction at steady state, what is the statement, or what is the relationship between this K1 and K2? That is the answer. Sorry, that is the one we have to find out. So we can try. So this is a very simple question. Just within 1 minute you can solve this out. I expect maximum answers in for this question, because as compared to the previous two questions, this is very simple. Okay, I will also start doing this. So in the question, it is given that the intermediate temperature, I'm writing it as T inter is equal to the average of the two sides, that is T1 plus T2. Okay, so we have to find out what is the uh, relationship between the thermal conductivities of these two materials, that is K1 and K2. So we know Q is equal to, means there is a heat transfer happening as you, or I'm writing it as heat flux because this is a composite wall and both the area will be same. So I can present in heat flux, that is Q double prime. That is Q double prime is equal to K times, that is K1 times T1 minus T inter divided by, what is the line? That is 2B. It should be equal to K2 times T inter minus T2 divided by B. This is the only one. The next rest is just mathematics. Is these
Answer is
two
D.
answer is
D1, sir. K1 equal to
D.
K2.
Yeah, that's right. So that is K1 T1. I am substituting this T inter T1 plus T2 divided by 2, which is equal to K2 times T1 plus T2 by 2 minus T2 divided by 1. Okay. So which is equal to K1 times 2 T1 minus T1 minus T2 by is equal to 2 K2 T1 plus T2 minus 2 T2 by 2. So that is K1 by 2 T1 minus T2 will be equal to K2 times T1 minus T2. K1 should be 2 times K2. I hope you are all are getting the same answer. How many of you got this answer? Okay, I hope everybody got this. So let's move on to that was a simple question. So let's move on to the next question. So this is a one-dimensional heat steady state conduction problem that is occurring in a plane wall with an internal heat generation, and the thickness of the wall is given as 50 mm, and a constant thermal conductivity is also given, and a temperature distribution we are assumed to take a quadratic form of a plus bx plus c x square, and the surface at x is equal to 0 has a temperature. The temperature at the sides or at one surface is also given, and the other surface experiences a heat transfer, a experience convection with a heat transfer fluid, with a fluid which is at 20 degrees Celsius and a convection heat transfer coefficient of 500 watts per meter Kelvin. Surface XL is well insulated. So one surface is well insulated, and we are we are asked to find out what is the volumetric heat generation rate. Okay. So you can start solving this. So I will just draw the schematic so it may be helpful for you. So when you get a question, try to draw the schematic. So we have a plain wall. So, and one surface, I'm taking this surface as insulated. And here we have a fluid which is flowing, that is TF, that is 20 degrees Celsius, and a heat transfer coefficient of 500 watts per meter square Kelvin. Okay. So I'm taking from here as x. So this is x is equal to 0 and x is equal to L. So the as per the question, the surface x is equal to L is well insulated, and the T0, that is this temperature is given as 120 degrees Celsius, and the temperature distribution and the thermal conductivity K thickness is also given, that is 50 mm, and the thermal conductivity K is also given as 5 watts per meter Kelvin. Okay. So, and also the temperature distribution T of x is given as A plus Bx plus Cx square. So these are the given things in the question. So next we need to find out what is the volumetric heat generation rate. Okay, I will also start with you. So first we have to write what the steady state one-dimensional steady state conduction equation with uniform heat generation. So it's always better not to by heart this. So just start with the general heat conduction equation, that is d square T divided by dx square plus d square T by dy square plus d square T by dou Z square plus q dot, that is I am writing this as heat generation, that is q dot by k is equal to 1 by alpha dot T by dot T. Okay. So this is a steady state equation. So this right hand side will cancel out, and also it's a one dimensional, so there is no variation in y and z direction. So but we cannot neglect the fourth term, that is because there is a heat generation that is happening. So our governing equation reduces to d square T by dx square plus q dot by k should be equal to 0. So as the temperature is only a function of one variable, we can replace the partial derivative with the ordinary differential derivative, that is d square T by dx square plus q dot by k is equal to 0. So this is the governing equation for this case. So this is our starting point. Okay. So next, we know we will apply the energy conservation. Okay. So that is what is energy conservation? E dot in minus E dot out plus E dot gen is equal to E dot E dot change in the energy within the system. So this is there is a steady state. So there is no energy that is coming in. So this is also zero. So we can say E dot gen, that is whatever heat is generated, should leave the wall. So Q dot, that is this is the volumetric heat generation rate. I hope you know this Q dot is the volumetric heat generation rate. So in order to convert it to the heat generation, we have to multiply it to the volume. So I am assuming that the area of the slab is A into the length. The length is already given. L is equal to, yeah, out, right? So what steady state? It should be, so whatever heat is generated, it should be convected to the fluid. So that is H A, that is the air surface heat transfer surface area A into T T0 minus TF. Okay. So this heat should be convected away for the steady state condition to satisfy. So this A and will get cancelled out. So the heat generation rate is H T0 minus TF divided by L. So H is already given, that is 500. The T0 is already given, that is 120. T of fluid is given 20. L is given 50. So what is this answer? What is the heat generation rate?
So 1000 kilowatt per meter cube.
1000.
1 megawatt. So you can say 1 megawatt. 1 megawatt per meter cube.
Yeah, 1000 kilowatt, or we can say 1 megawatt per meter cube. I hope everybody got this answer. So just we are applying the basic principles, like we started with the basic energy conservation equation. Then we strike out the terms that are not applicable because the question is already given, it's a steady state. And in this system, there is no heat that is coming into the system. So whatever heat that is generated within the wall, it should be convected out. That is, from that, we got what is the heat generation rate. So
Sir,
next question,
excuse me, sir.
yeah,
What you have written on the right hand side of energy conservation, this EST.
that is the change internal change in means change in energy within the wall. Like if there is any change of temperature, like this term, basically this is this one, right? From this only we are getting this. So within the plane wall, there is no change in the temperature at with respect to time.
So is this term accumulation?
Yeah, we can say it's like no accumulation.
Okay.
So so in the question number, so it's a next question is also a continuation of the question number 4. So in this question, we have to determine the coefficients A, B, C. Means the temperature is given as a function of the spatial coordinates, that is x, that is t is given as bx plus c x square. So we have to find out what is this coefficients A, B, and C. Okay. So, so for that we will use this equation, that is d square t divided by t x square plus q dot by k should be equal to 0. So what is dt by dx is equal to b plus 2cx, and d square t divided by dx square is equal to 2C, right? So 2C plus Q dot by K should be equal to 0, right? So we can calculate C. What is C is equal to minus Q dot by 2K minus 10 raised to 6 divided by 2 into what is the thermal conductivity is 5. So it will be minus 10 raised to 5 Kelvin or degrees Celsius per meter square. Okay. So just we substituted the values. So we got C. Now we have to find out both A and B. For that we are using another boundary condition that it is
Sir,
given
at
that
x equal to 0, at
yeah,
x equal to 0, t0 equal to 120 degree, and sir, as the slab is insulated at x equal to L, so dou t by dou x at x equal to L equal to 0.
yeah. That is what I am
Flex
going
equal to
to
0, sir.
apply next. Yeah. At insulated wall, that is dt by dx at x is equal to L should be equal to 0. So what is dt by dx? That is b plus 2cx should be equal to 0. So what is b? Can you please tell? Minus 2cx. That is minus 2 into again minus 10 raised to 5 into x is how much? 5 So 5 into, sorry, 50. 50 into 10 raised to minus 3. You will get B as 10 raised to 4 Kelvin per meter. Am I right? So I hope you also got this answer. Anybody got
Yes, sir,
this?
we got it. Yes, sir.
Okay. So what then next is like just we knew. So B we found B also. So next it's very simple, that is T is equal to A plus B x plus C x square. So at x is equal to 0, it's already given. T T at x is equal to 0 is equal to T0, which is 120 degrees Celsius. So as it is degrees Celsius, you can replace all this with degrees Celsius. So A is equal to 120 degrees Celsius. So like this also questions can come, like we have to find out what are the coefficients of the temperatures. So this was like we have to apply appropriate boundary conditions to find out the to find out the constants A, B, and C. Okay, so let's move on to the next question. So we have an asbestos pad of length 15 centimeters, which is wire in cross section, measuring 5 centimeter on one of its sides, means on one side at its small end, increasing linearly to 10 centimeter on a side at the larger end. If the small end is held at 600 Kelvin and the large end at 300 Kelvin, what what will be the rate of heat flow if the other four sides are insulated? So we can assume 1D heat conduction with the thermal conductivity of 0.173 watts per meter Kelvin. So that is the question. So this is a little bit you have to think and do. So I will give you some time, some 5 minutes for you to solve. After that, I will start solving. So the one thing you have to consider here is the area is not constant. So the area is varying from one side to another side. So you have to consider that concept. And means the relation how the area is increasing on one side to another side is also given. So please please attempt these questions. Little bit, if you think a little bit, you will get this. Okay, I will also start doing. So I need input from you. So as we, if you notice, you can see the heat transfer takes place from left to right. I'm writing it as Q. Okay. Okay. So the area is varying, right? So at any x, what is the area? So I'm writing at any x, the area is Lx square, right? This is a square. So our task is to find out what is Lx, that is the variation of length with respect to x. So it's already given that the L is varying linearly from 5 centimeter to 10 centimeter. So let's assume Lx is equal to some a plus bx. It's a linear variation, right? So at x is equal to 0, Lx is equal to 5 centimeter or 0.05 meters, right? So 0.05 is equal to A. So we got one constant. Next, at X is equal to L, that is 15 centimeter, that is 0.15 meters. Lx is equal to 0.1 meter or 10 centimeter. So 0.1 is equal to 0.05 plus, sorry, yes, B times 0.15. So B is equal to, if you calculate 0.05 divided by 0.15, it will become 1 by 3. So we got the expression Lx is equal to we got the expression Lx is equal to A plus Bx. So A is equal to 0.05 plus x by 3 in meters. So area is equal to 0.05 plus x by 3 the whole square. Okay. So what is heat transfer? A Q at any x is equal to minus K Ax dt by dx. Okay. At any x. So our aim is to find out what is Q. Okay, or Q. So at any x, so Q is should be equal to minus K Ax dt by dx, which is equal to minus K times 0.05 plus x by 3 the whole square dt by dx. So Q is constant, K is constant, T is varying. So it's like it's a now it becomes function of T and X. Okay. So we will write Q times dx divided by 0.05. We will separate the variables, is equal to minus K dt. So now we can integrate from x is equal to 0 to 15 or 0.15, and the temperature is also given, that is from 600 to 300. Okay. So K is already known, so we can write K times integral 0 to 0.15 dx divided by 0.05 plus x by 3 the whole square is equal to K is already given. How much is K? 0.173 T. It's simple integration for T, so we can write minus T, like it's 300 and 600. So if we integrate 0 to 0.15 dx 0.05 plus x by 3 the whole square will be equal to 0.173 into 300. So now the only thing you need to do is how to integrate this value. So I hope you know how to integrate. So I'm not doing the full integration. I will just give you a clue. So you can convert this into a variable like t, and you can take dt is 1 by 3 dt, and you can substitute it back, and you can also like change the limits according to the t value. So if you do this integration, if you have any doubt, I will do this integration at last. So because we have to complete it, all the questions. So Q is equal to, you can try this integration, and if you have any doubt, you can ask in the next class. So Q is equal to, I will get 1.73 watts. Okay. So I hope up to this it is clear. So only you may have some doubt about this integration. This integration is simple. Like it's a plus two level integration only. So you can, I hope you can do this integration. So anybody got this answer before me?
Yes, sir.
Yeah, fine. So like this is one case of area. So you can expect say same question with different functions of area. Like area can be like the it can be exponential function, then quadratic function, logarithmic function. So questions can be like that. So if you take some standard textbooks like in Coursera or Central, you can find similar kind of questions. So so the same question. So like if thermal conductivity is also varying, the same question in the earlier question, like we have the constant thermal conductivity, but in this question, the thermal conductivity is also is a function of T. That's the only difference. So please try solving this. So I will also start solving. So the heat is the minus K AX. Now it's we cannot write it as K. It's a function of T. So minus K T AX dt by dx. Okay. So Q is equal to minus K0 1 plus beta T. What was the function of A? Yeah. 0.05 plus x by 3 the whole square dt by dx. So just we can easily subtract the variables like q is q into dx divided by 0.05 plus x by 3 the whole square is equal to minus k0 1 plus beta t dt. Now you can integrate from 0 to 0.15 and this from 600 to 300. Okay. So the left hand side integration is almost same as that of the previous. So only change is right hand side. So minus k naught t plus beta t square by 2. You have to give the limits 300 to 600. So if you do this, if you apply this limit and put beta is equal to, it's already given 1.95 into 10 raised to minus 4, you will get a value of around 326.325 k naught. Okay. So this integration you can do. So at
The
last
answer is 1.50.
yeah, the answer is 1.50 watts. Okay. So this was a question was similar as earlier. The only difference is now the thermal conductivity is also a function of T. So this much, this up to this is only the heat. We need the heat transfer knowledge. Rest is just mathematics. Okay. Now we will go to the next question. So it's like a two-dimensional body. The gradient at surface A is found to be dou T by dou Y is 30 Kelvin per meter. And we have to find out what is the gradient dou T by dou Y and dou T by dou X at surface B.
Sir, is the answer is C?
The answer is, yeah. The answer is D. If anybody others got this answer? Okay. So this question, whatever heat that is entering, that is E N, should be equal to E out. Right. So the heat flux at A should be equal to, or not heat flux, the heat that is entering through the surface A, that is QA, should be equal to QB. That is the basic point you have to find out. So what is QA? Minus A area of at A. Like we can take unit depth, like unit depth into dou T divided by dou Y. Okay. And QB is equal to minus K A at area at the B dou T divided by dou X. This is at A, this is at B. So you know the gradient, the heat flux or the heat transfer should be always normal to the isothermal surface. Okay, that is the main concept here. So if we can equate these two, so K is same, so area is like here it is 2, I am taking it as unit depth, dou T divided by dou Y, it's already given 30, should be equal to, so I cancelled out, it's this K, and this one is 1 into 1 to dou T divided by dou X at B. So dou T divided by dou X at B is equal to 60 Kelvin per meter. So here the heat transfer will be like this. Here the heat transfer, the direction of heat transfer will be, it's always, it will be normal to the isotherm. Okay. So now we can see in this surface. So one derivative we found out. Dou T by dou X at B we found out. So will there be any gradient in Y direction? Because this is the iso surface, so isothermal surface. So whether heat transfer will take like this? No. The heat flux or the heat transfer should be, heat flux should be always normal to the isotherm. Isotherm, I think you know, it's a constant temperature surface. So there won't be any component of dou T by dou Y. So the answer is, as one of you said, it is C. Okay. So let's move on to the next question. So we have a room which has an exterior wall of 20 mm thick sheathing with thermal conductivity 0.15. To reduce the heat losses in the winter, the owner decides to encapsulate the room wall with an insulation of 20 mm thick with a thermal conductivity of 0.018 watt per meter Kelvin. This insulation is covered with a 4 mm thick glass of thermal conductivity 1.2 watt per meter Kelvin. Determine the reduction in the heat loss with insulation and glass. The interior and exterior temperatures and the heat transfer coefficients are also given. So we have to find out by adding this insulation how much reduction in the heat transfer was attained. We can start attempting. So the insulation, so like initially there was only, you consider two cases. Initially there was only wall, there was no insulation, and you find out the heat transfer. And next, in the second case, you find out the heat transfer with the insulation and also the glass. Okay, then you change, you find out the percentage reduction in the heat loss. That is how you have to solve this question. So can you please tell what is the heat flux without insulation, means with just the exterior wall? Okay, I will also start solving this question. So basically the case one we will solve. No insulation. So we have a wall of around 20 mm thick with the thermal conductivity of around 0.15, and the interior is at 23 degrees Celsius, and the heat transfer coefficient at interior is 4 watts per meter square Kelvin. The exterior is minus 15 degrees Celsius, and the heat transfer coefficient is 23 watts per meter square Kelvin. So first we will find out the heat flux with this. So the heat flux is equal to delta T divided by R. So what is R? We have Ti here, and we have a convection resistance of 1 by Hi, then we have a conduction resistance of L by K, and then we have a convection resistance of 1 by Ho. So Q heat flux is delta T, that is delta T 23 minus of minus 15 divided by 1 by what is Hi 4 plus 1 L is 0.02 by K, what is thermal conductivity 0.15 plus 1 by Ho 23. So this will be 38 divided by what is this value? This value will come out to be around 0.4268. So anybody calculated this resistance? What is this heat flux? Can you please calculate and say?
Sir, 89.03.
Yeah, almost 89. I am getting 89.6. So there may be some small. So what is the resistance? Is it 0.4268?
Yes, sir.
Yeah. So it's 89 point. How much?
03, sir.
03. Okay. So the next case we will consider with insulation. So we have a two-layer insulation for this. First, we have the brick. Okay. Then we have an insulation, and again we have a glass insulation. Okay. So this K is given us around how much? 0.15. This K is given us what is the insulation 0.018 watt per meter Kelvin, and the glass it is given us 1.6 1.2 watt per meter Kelvin, and the length of this L1 is 20 mm, L2 is 20 mm, L3 is this I am writing 1, 2, and 3, 4 mm. So now let's write the resistance here also T1, H1, T2, H2, or HO. So the resistance, what is the resistance? We have convection resistance of 1 by Hi. Then we have a conduction resistance from the brick L1 by K1. Then again we have a conduction resistance of this insulation L2 by K2. Then again we have a conduction resistance of glass L3 by K3. Then we have a convection resistance of 1 by Ho. So can anybody calculate and say what is this resistance? R is equal to 1 by Hi plus L1 by K1 plus L2 by K2 plus L3 by K3 plus 1 by Ho. H1 is how much? 1 by by 4 plus L1 is 0.02 by K1 0.15 plus L2 is again 0.02 divided by 0.018 plus 0.004 divided by 1.2 plus 1 by HO is 23. So what is this answer? This R?
So 1.5412.
Yeah, 1.5412 Kelvin per. What is this heat flux? Can you tell delta T?
24.65. 24.65.
24.65 watt per meter square. What is the percentage reduction? You can calculate 89.66 minus 24.65456 divided by or 0.03 as you said. So by 89.03 into 100. So in percentage, how what can you please say what is some approximate around? Is it close to some 72%?
Yes, sir. 72.3%.
Yeah. So you can just see the physical significance of this, like how much with the insulation, how much reduction in the heat transfer is we can have with by using insulation. That is the main purpose of using our insulation. So in later you will study different insulation like critical radius of insulation and all in the carbonic section. So of course problems related to that we will solve in that area. So this is like uh, this is also like a composite wall, right? So the basic concept is composite wall, but the physical significance of this problem is like uh, the to give to show you the importance of how the insulations can be used to reduce the heat loss or the heat transfer. That is the physical significance of this question. So this is our last question. So this is a question almost similar to that of the previous ones. Like so, if you have carefully understood the previous 10 questions, you can easily solve this. So this question you have to solve and give the answer. It's a steady state one dimensional conduction occurring in a rod of constant thermal conductivity K and the variable cross section area. The cross section area relationship is already given, and the volumetric heat generation is also is not constant. It's a function of x. What is the expression for the heat flux when the left face and the lateral surface of the rod is well insulated? Anybody got the answer?
Sir, is the answer A?
Answer? Yeah, yeah. The answer is A. Okay, so I will solve this. So we know it's already given Ax is equal to A0 e raised to Ax, and the heat generation Q dot is equal to Q0 dot e raised to minus Ax. Okay, so now we will write the general equation, that is minus, sorry, d by dx of k Ax dt by dx plus Q dot into Ax should be equal to 0. So this is a part of like we derived in the one-dimensional heat conduction equation. So now the k is constant, so we can write d by dx of Ax. So this is what we need, right? It is the what is the expression for heat flux? Like
Can you elaborate this equation because we have not studied this equation?
yeah, yeah, I will elaborate at last. Okay. Otherwise, I will. It's better to. So we have. I am considering a strip. Right. So some heat is flowing. That is Qx. I'm right. Qx plus dx. Okay. So this is an elemental strip of length delta x. And there is some heat generation that is happening, that I am writing it as Q dot into Ax into delta x. So if we give the energy balance like Qx plus Q dot Ax delta x should be equal to Qx plus dx. I hope this is clear up to this much. So now Qx minus Qx plus dx or delta x is equal to plus Q dot Ax into delta x should be equal to 0. So Qx minus Qx plus delta x divided by delta x plus Q dot Ax should be equal to 0. Okay. So what is this? When delta x tends to 0, we can write it as the rate of Qx divided by dx plus Q dot Ax. This is minus. So this is how that equation came. I hope it is clear to you.
Yes, sir. Thank you.
So now I hope you can solve this question, right? So I am giving you as a homework to you. So one of you solve. So the others can also try. And if you have any questions, like I think this This problem is straightforward. It's like putting into this equation and you will get the heat flux. Okay, or the heat transfer. So I'm giving this as a assignment to you. So please, in the next class, please try to solve this and come. And ask the for verification. The answer is first one, that is 2x is equal to a0 q0 into a0 into x. And if you have any doubt, I will solve it in the next class. Just it's a like two-step only. Okay. So I hope this session was helpful for you. So I just need some feedback from you. Just a minute. Okay. Whether this session is useful for you or like we should continue like this with solving some different. I am trying to get different questions, like different types of questions so that you will get a exposure. Okay. So any of you can share your experience so that I can improve in the next class.
Yes, sir. It was so helpful to us. Like, you can sir, like, the level of question, if improved, that would be help us so much.
So you want more level means higher level
Yes, sir. Yes, sir.
questions. Okay,
Yes, sir.
fine. I will consider.
Like, sir, for varying area, for contact resistance, and for cylindrical questions, all
Yeah,
those questions,
that is
they would be
coming.
there.
So because the like what how we are doing is in week one that concepts are not covered, even though the
Yes,
week
sir. Yes,
two and week three sessions are live. So in that week two and week three, sorry, week one, this contact resistance, conduction through radial systems, and all are not covered. That's why I didn't put that question. So in the coming classes, we will surely discuss that kind of questions.
sir. Okay, sir. Fine. This was
So,
so helpful for us.
okay, so I will try to increase the level of questions. So I cannot increase to a very much high level because we need to solve a couple of questions. Right? So I will try to cover maximum questions so that you will get a broad idea of the week that week's lecture.
Yes. Thank you, sir.
So anybody else wants to share the experience? Okay, then we will stop this session here, and I hope uh, it's like on every Monday. It's from almost 6 to. We'll start at 6 o'clock. It will continue for 12 weeks. Like it's like for 12 weeks lectures. So see you at the next week, next Monday. Have a nice week ahead. Thank you. Thanks for listening. Thanks for the time. So you can. I hope you can leave the meet.
Thank you, sir.
Yeah. Thank you.